Induction. The well-ordering principle says that every non-empty subset of natural numbers has a least element. For example, let's look at the set of natural numbers itself. The least element of this set is 0. Theorem. The principle of mathematical induction. The principle of mathematical induction says the following. Let S be a set of natural numbers such that 1, 0 is in S, and 2, for all k and n, k in S implies k plus 1 is in S, then S is the set of natural numbers. Before proving the principle of mathematical induction, let's just talk for a minute about how it works. The principle of mathematical induction works like a chain reaction. So starting with 0 in the set S, which is the first thing that's given in the statement of the principle of mathematical induction, and using the second condition with 0 substituted for k, we have that if 0 is in S, then 1 is in S. So we have the compound statement, 0 is in S, and if 0 is in S, then 1 is in S. I just switched here to our logical notation from lesson 1, where we use this wedge-shaped symbol for AND. So if we let P be the statement 0 is in S and Q the statement 1 is in S, then we have P and P implies Q is a true statement. So I'll put a T under the conjunction symbol to indicate that this statement is true. And remember that a conjunction is true means that both statements are true. So P is true and P implies Q is true. Since both P is true and P implies Q is true, Q must also be true. So Q in this case is 1 is in S. So it follows that 1 in S is also a true statement. We can now apply the same reasoning by replacing K by 1 to get that 1 is in S. And using condition 2, 1 is in S implies 2 is in S to give us that 2 is in S. And we can repeat this reasoning to get that 3 is in S, and so on. 4 is in S, 5 is in S, and so on, that every natural number is in S, so that S is equal to the set of natural numbers. Okay, let's do a rigorous proof now of this theorem. We're going to prove the principle of mathematical induction by contradiction using the well-ordering principle. So before we write out the proof, let's just go over how a proof by contradiction actually works. First, we assume the negation of what we are trying to prove. In this case, since we're trying to prove S is equal to N, we're going to start with S not equal to N. We then use a logically valid argument to derive a statement which is false. Since the argument was logically valid, the only possible error is our original assumption. Therefore, the negation of our original assumption must be true. Okay, so let's start the proof with our opening statement. Let S be a set of natural numbers such that 0 is in S, that's condition 1, and such that whenever k is in S, k plus 1 is in S, that's condition 2. Assume toward contradiction that S is not equal to N. So again, we're trying to prove that S is equal to N, but we're going to do it by contradiction, so we assume the opposite, which is that S is not equal to N. Let A be the set of k and n such that k is not in S. So A is the set of natural numbers not in S. Okay? Since S is not equal to N, A is non-empty. right? Because A is the set of things not in S. Since S is not all of n, there must be some things in the set A. Note that in reality, A is actually empty because the conclusion of the theorem is that S is equal to n. So there's nothing that's not in n, which means there's nothing in A. However, our wrong assumption that S is not equal to n tells us that this set A actually has something in it. This is an example of a false statement that was derived from a logically valid argument. This false statement occurred not because of an error in our logic, but because we started with an incorrect assumption. Our incorrect assumption being that S is not equal to n. Okay, so since A is non-empty, by the well-ordering principle, A has a least element. Let's call it little a. Okay, so we used the well-ordering principle here to get a least element of capital A. Okay, again, although the argument that A has a least element is logically valid, A does not actually have any elements at all. We are working from the wrong assumption that S is not equal to n. Now, A is not 0 because 0 is in S and A is not in S. Right? A is an element of capital A, which means precisely that little a is not an element of S. And 0 is in S by our assumption, right? That's condition 1. So A minus 1 is a natural number, right? Because A is not equal to 0. Whenever A is not equal to 0 and A is a natural number, 1 less than it is also a natural number. Letting K equal A minus 1, we have that A minus 1 is in S. Because A is the least element not in S, since A minus 1 is smaller, it must be in S. So therefore, K is in S, because K is equal to A minus 1. This is just a direct substitution. It follows that K plus 1 is in S. Again, by substitution, A minus 1 plus 1 is in S, and that's equal to A, so A is in S. But little a is in A, which means that A is not in S. This is a contradiction, and so S must be equal to the set of natural numbers. Again, since the argument was logically valid, the only possible error here is our original assumption that S is not equal to n. Therefore, the negation of our original assumption must be true. That's how we got that S is equal to n. The principle of mathematical induction is often written in the following way. Let P of n be a statement, and suppose that 1, P of 0 is true, and 2, for all k and n, P of k implies P of k plus 1. Then P of n is true for all n and n. Okay, this is equivalent to our original statement of the principle of mathematical induction. It's not too hard to show, and you may want to try and take a few minutes to actually write out proofs that these two things are equivalent. A proof by mathematical induction involves two steps. There's a base case where we prove that P of 0 is true, and the inductive step where we assume that P of k is true and use this to show that P of k plus 1 is true. P of k being true is known as the inductive hypothesis. Let's look at an example. Use the principle of mathematical induction to prove that for all natural numbers n squared minus n is even. So first, I just want to go over this notation here. N squared means n times n. You're multiplying n by itself. Also, subtraction, when we subtract, that means we add the additive inverse. So n squared minus n is equal to n squared plus the negative of n, or the additive inverse of n. Okay. Let's start with the base case, which is k equals 0. Well, 0 squared minus 0 is equal to 0, which we can write as 2 times 0. That shows that 0 squared minus 0 is even. Right? Remember that even means 2 times an integer. Since 0 is an integer, 2 times 0 is an even integer. The inductive step. Let k be a natural number and assume that k squared minus k is even. Then we can write k squared minus k as 2b for some integer b. Now, okay, let's go through this step by step. So we want to show that k plus 1 squared minus k plus 1 is even, right? Okay, so this is equal to k plus 1 times k plus 1 minus 1. In this step, we're using left distributivity, right? If you're having trouble seeing this, try working backwards and making the substitutions x equals k plus 1, y equals k plus 1, and z equals negative 1. Let's look at the details here. We then have k plus 1 times k plus 1 minus 1 is, well, first let's rewrite subtraction as addition. So we rewrite that minus 1 as plus negative 1. And we'll make these little substitutions here, x, y, and z, to get x times y plus z. And now we use left distributivity to write that as xy plus xz. And substitute back. Remember that x is k plus 1, y is k plus 1. Again, x is k plus 1, and z is negative 1. And when we multiply something by itself, that's the same as squaring it. So we get k plus 1 squared. And we can use commutativity of multiplication here to switch the k plus 1 and the negative 1. And finally, we could rewrite plus negative 1 times k plus 1 as minus k plus 1. Okay, next step is we rewrite k plus 1 minus 1 as k plus 1 minus 1. And here we're using associativity of addition. We have k plus 1 minus 1 is equal to k plus 1 plus the negative of 1, which is by associativity k plus 1 plus negative 1, which is k plus 1 minus 1. Okay, next step, we could rewrite 1 minus 1 as 0. And here we are using the inverse property for addition. 1 minus 1 is 1 plus negative 1, which is 0. Okay, and now we can write k plus 0 as k. Here we are using the identity property for addition, right? K plus 0 is equal to k. And this is equal to k squared plus k. And we're using right distributivity here. K plus 1 times k is k times k plus 1 times k. K times k is k squared. And 1 times k is k because 1 is multiplicative identity. Okay, and now I'm going to rewrite k squared plus k as k squared minus k plus 2k. Okay, what happened here? That's kind of weird, right? Where on earth did I get this expression from the previous one? Well, here I'm using what I call the standard advanced calculus trick, which I abbreviate as SACT. Now, I call it the standard advanced calculus trick because I first noticed this trick being used over and over again when I was taking an advanced calculus course, but the trick itself is used in all branches of mathematics. The idea behind the trick is very, very simple. If you need something to appear, put it in, but then correct it by performing the opposite. Okay, so in this case, in order to use the inductive hypothesis, which is the k squared minus k being equal to 2b, we need k squared minus k to appear. So I make it appear by putting in that minus k, but then I immediately put a plus k next to it to undo the damage that I just did, right? So I could rewrite k squared plus k as k squared minus k plus k plus k. And now I simply group together the k squared minus k because that's the expression that I wanted to appear. and then I combine the k plus k as 2k. And that's where I got that expression. Now we can replace that k squared minus k by 2b. Right? So we get 2b plus 2k. And that's equal to 2 times b plus k. And here we're just using left distributivity. And I'm going to sum all this up by just saying here we use the fact that the set of integers together with addition and multiplication is a ring. So I'm not explicitly writing out every single property in the proof itself, just because that would get a little bit tedious. Finally, since z is closed under addition, b plus k is an integer. So we just showed that k plus 1 squared minus k plus 1 is even. Okay, so we proved the base case and the inductive step, and now we can say by the principle of mathematical induction, n squared minus n is even for all n in n. Sometimes a statement involving the natural numbers may be false for 0, but true from some natural number on. In this case, we can still use induction. We just need to adjust the base case. Let's look at an example of this. Use the principle of mathematical induction to prove that n squared is greater than 2n plus 1 for all natural numbers n greater than or equal to 3. Okay, the base case, which in this case would be k equals 3, because that's where we're starting from. We have that 3 squared is equal to 9, and 2 times 3 plus 1 is 6 plus 1, which is 7. So 3 squared is in fact greater than 2 times 3 plus 1. Okay, now the inductive step. Let k be a natural number with k greater than or equal to 3, and assume that k squared is greater than 2k plus 1. Then we have k plus 1 squared is equal to k plus 1 times k plus 1, which is k plus 1 times k plus k plus 1 times 1. And here we used left distributivity. That's equal to k squared plus k plus 1. We used right distributivity to rewrite k plus 1 times k as k squared plus k. Here are the details. K plus 1 times k is k times k plus 1 times k, which is k squared plus k. Notice how we used the multiplicative identity property here to write 1 times k as k. And to write k plus 1 times 1 as k plus 1, we again use the multiplicative identity property here. Notice also that we're implicitly using associativity of addition because we didn't use any parentheses here. Associativity of addition allows us to drop all the parentheses whenever we're adding a bunch of things. Okay, now this expression is greater than 2k plus 1 plus k plus 1. Here is where I'm using the inductive hypothesis, that k squared is greater than 2k plus 1. That allows me to replace k squared by 2k plus 1 as long as I use a greater than symbol instead of an equal sign. Okay, now this is equal to 2k plus 2 plus k plus k. Here we used commutativity and associativity of addition in order to pass that 1 through those k's and then to combine it with that other 1. Okay, now this is equal to 2 times k plus 1 plus k plus k. And here we're simply using left distributivity. Now this is greater than or equal to 2 times k plus 1 plus 1, because k plus k is greater than or equal to 3 plus 3. Remember, we assume that, which is equal to 6, and 6 is greater than or equal to 1. Okay, so since we proved the base case and the inductive step by the principle of mathematical induction, n squared is greater than 2n plus 1 for all n in n with n greater than or equal to 3. Another example. Use the principle of mathematical induction to prove that for every natural number n, there is a natural number j such that n is equal to 2j or n is equal to 2j plus 1. Base case, k equals 0. 0 is equal to 2 times 0. The inductive step. Suppose that k is a natural number and there is a natural number j such that k is equal to 2j or k is equal to 2j plus 1. If k is equal to 2j, then k plus 1 is 2j plus 1. If k is equal to 2j plus 1, then k plus 1 is 2j plus 1, which is using associativity of addition, 2j plus 1, which is 2j plus 2, and that's equal to 2 times j plus 1 using left distributivity. And again, I'll sum this up by saying here we use the fact that n plus times is a semi-ring. More specifically, we used associativity of addition in n and distributivity of multiplication over addition in n. I spelled it out this time just so that you could see we're really only using semi-ring properties. Since the set of natural numbers is closed under addition, j plus 1 is a natural number. By the principle of mathematical induction, for every natural number n, there is a natural number j such that n is equal to 2j or n is equal to 2j plus 1. In fact, the analogous result for integers is true as well. In other words, for every integer n, there is an integer j such that n is equal to 2j or n is equal to 2j plus 1. Now, we won't need induction to prove this, but it fits in with what we're doing, so let's go ahead and write out the proof. We already proved the result for n greater than or equal to 0, so we just need to do it for n less than 0. If n is less than 0, then negative n is greater than 0. And so, by the previous result, there is a natural number j such that negative n is 2j or negative n is 2j plus 1. If negative n is 2j, then n is 2 times negative j. Okay, I admittedly left out some details here. You may want to fill those in. Since j is a natural number, negative j is an integer. Now, if negative n is 2j plus 1, then n is negative of 2j plus 1. Again, you may want to fill in these details. And that's equal to negative 2j minus 1, which is negative 2j minus 1 plus 1. Notice how I threw in what I needed and then undid it. That's the standard advanced calculus trick. And now I combine what I need. So we get negative 2j minus 2 plus 1, which is equal to 2 times negative j minus 1 plus 1. Here we use the fact that z plus times is a ring. And since z is closed under addition, negative j minus 1 is equal to negative j plus negative 1 is an integer. If n is equal to 2j, we say that n is even, and if n is equal to 2j plus 1, we say that n is odd. An integer, n, cannot be both even and odd. Let's prove this. Let n be an integer. Suppose, toward contradiction, that n is both even and odd. So there are integers j and k such that n is equal to 2j and n is equal to 2k plus 1. Then 2j is equal to 2k plus 1 because they're both equal to n. So we have 2 times j minus k is equal to 2j minus 2k using left distributivity. Now we can just do a direct substitution here. Replace 2j by 2k plus 1. And then use associativity of addition to rewrite that as 2k plus 1 minus 2k. Using commutativity of addition, we have 2k plus negative 2k plus 1. Associativity again to get 2k minus 2k plus 1. Now 2k minus 2k is 0, and 0 plus 1 is 1. So 2 times j minus k is equal to 1, but 2 does not have a multiplicative inverse in the set of integers, and so this is a contradiction. I want to finish up with one more theorem. The product of two odd integers is odd. Again, this doesn't use induction, but it's a nice way to finish this section because we're going to need this result for the next lesson. Let's write out the proof. Let m and n be odd integers. Then there are integers j and k such that m is 2j plus 1 and n is 2k plus 1. So m times n is 2j plus 1 times 2k plus 1, which is 2j plus 1 times 2k plus 2j plus 1 times 1, using left distributivity there. That's equal to 2k times 2j plus 1 plus 2j plus 1. For the first term, we used commutativity of multiplication. For the second term, we used the fact that 1 is the multiplicative identity. Okay, that's equal to 2k times 2j plus 2k plus 2j plus 1. Okay, now we can use associativity to rewrite 2k times 2j as 2 times k times 2j. And using distributivity, we can rewrite that left expression as 2 times k times 2j plus k. Now some associativity here to get 2 times k times 2j plus k plus 2j plus 1. And distributivity once more to pull out that 2. So here we use the fact that the set of integers together with addition and multiplication is a commutative ring. Since z is closed under addition and multiplication, this expression k times 2j plus k plus j is an integer. Therefore, m times n is odd.